Alright, we're going to keep the fun going here, and we're going to finish up the electric potential problem for the uniformly charged disk. So this is part 2. Part 1, hopefully you've digested that already. We ended up with this expression at the bottom. I'm going to copy that down again, and now we got to just solve it. Okay. So that's the integral that we're going to have to deal with. And the way that we're going to do this is by substitution. This is a good practice. And if you want to try this on your own, maybe take my hint that I'm about to give and then pause the video and try to do it on your own. I think you'll get more out of it that way since we've already done substitution in class. So my substitution here is going to be, I'm going to use u as a variable that I substitute, and I'm going to make u equal to r squared plus x squared, because I've got that down here and I want to simplify it. So remember, the second thing that you do then is you take a derivative, sort of, and when you do the du, you're going to end up with 2r dr, so it's like taking the derivative on this, plus 0, because x is kind of like a constant in terms of what this integral is doing. So that allows me to say that dr is going to be equal to 1 over 2r times du. Okay. Now that might not look good to you, but it's great, because you're going to simplify this down here, and you're also going to divide out the r that's up there. So this is a great point to pause the video and see if you can take the next few steps on your own. Otherwise, I'm just going to keep on going here. Okay, so this is going to end up being then that times the original r that was up here in the first place with my du all over u to the 1/2. Okay, and so you can see that the 2's cancel out, the r's cancel out, and you're left with this. Which is like pretty simple and a pretty easy integral to take if you think about just, finding the antiderivative of u to the negative 1/2, the way we've talked about it. So let's do it. When you integrate this, you have to you add 1, so it's just 1/2, and then you do 1 over positive 1/2 times u to the positive 1/2. So I will be exceedingly detailed in how I write that. So you check that, right? This should be the antiderivative of what we have in the integral. And of course that just becomes 2kq over r squared. And then u, I'm not going to write u again, I'm simply going to write r squared plus x squared, right, because that was our substitution. And so there, I just solved the integral by substitution. So this is what we get from doing that, which is pretty nice. Now remember, we did have this was a definite integral in the beginning, and now I've gotten it back in terms of r. I can put the endpoints back on. Okay, so this is like 0 equals r, and r equals r. Alright. Then what we do is we're going to evaluate. So I'll take 2kq over r squared. And again, I would say this is a great time to pause the video, see if you can get through this, right? Can you put the endpoints in? Otherwise, I'm just going to keep on going. And so we're going to have final minus initial. So we'll have this minus the initial 0 squared plus x squared and there we've taken care of our endpoints. So it's final minus initial. Remember, r is the variable, and you're plugging in 0 and uppercase R. Okay. So we've got that. Of course, this just becomes x. That's nice. And if you look at what you have over here, you've got k over r squared. And hopefully you remember that, I'm sorry, q over r squared. That you hopefully remember that q over pi r squared was actually sigma, right? So we can do a clever little substitution here. Like that. So if you don't know where that comes from, take a second. Remember this. Right? And see if that works out. So does that should allow us to take that out and replace it with what we have here. Okay? Everything else is the same. And I'll write it with the x in there. Okay. So I think I did that right. Yeah, and we're just about done. I'm going to do one other nice thing here. Will come up. K is going to be 1 over 4 pi times permittivity. Sorry, it's a little bit tedious to multiply all this stuff. But I'm going to use that to get to something which is kind of simple here. Out in the front. Okay. And this is going to be our answer. Okay. So again, it's not very pretty. However, one thing that you might be noticing is that if you look at this term that's out in front, that should look familiar to you. If you recall, for an infinite sheet of charge, the electric field was given by that term. Okay? And so that should be kind of like making you think, well, that's interesting, because the disk isn't infinite, but it is kind of like a sheet. It's a two-dimensional plane. And so we're getting this term that's popping up in here. And the other thing is that this isn't electric field, this is potential, right? So you wouldn't expect the answer to simply be something like that. Potential is going to be field times a distance. So all this stuff in here, if you think about it, it has the dimensions of length. Right? Because you've got length minus length. And so this expression for the potential is actually kind of making a little bit of sense here, because we learned that the difference in potential is something like that for a uniform field. Okay? Now, I am not saying that this is a uniform field. It's not. The disk is not infinite. But I'm making the argument that it's kind of starting to look like a potential that you would expect from a sheet. Okay? And it goes a little bit beyond, I think, what I want to do with this video. But it's pretty easy to show that if you make R infinity, that you can actually show that all that stuff kind of disappears, and you can show that that the potential, that this more or less is going to go just down to x. So your potential is going to be like V is something like that. And that's a lot like the expression that we saw for the infinite sheet. So I'm not going to prove this to you because it gets into a little bit beyond where we are right now. But maybe I'll show it to you in a few more lessons, how that comes about. So that's what you got for this. And right, one thing to kind of notice, again, is to think about what happens maybe when x is equal to 0. So that would be, what if you were right in the middle of the disk, right there? And all this stuff does simplify quite a bit. And it would drop down to basically an expression like so, which I hope you can agree with. Just checking my math here. Yeah, that looks good. So that might be something that's useful. Notice that answer here, this is equal to v, right? V at x is equal to 0. Notice that is not infinity, right? That this is a finite value. And so, like, this disk is not infinite, so it doesn't have an infinite amount of charge. It has a fixed amount of charge. So the potential actually just goes up to some value and does something like that. You could always graph this in Desmos. It's kind of interesting if you want. I don't know if that's necessary, but if you really want to, go ahead and try it out. But you should see that the graph actually crosses the axis at that point. So I'm going to stop here, and you know, the idea is that we successfully came up with an expression for the potential created by the disk. Again, do not memorize the final result. The purpose of this was to kind of give you the idea of the method that we use when we find a solution by integrating charge.